Welcome to After Hours Engineering, Episode 13. With the ISA pretty much complete, we're ready for more complex programs that'll further exercise the ISA. For example, counting, shifting, loading, logic, jumping, branching, subroutines, comparing two strings, or even the Fibonacci sequence. However, working with GTK Wave is cumbersome when inspecting large and complex and long-running programs. Yet there's another way to view a softcore processor, and that is via a console program. And for that, we're going to use NCurses. NCurses is a relatively old API, but it's still in use today, and it can do exactly what we need it to do. So let's go. With NCurses, instead of viewing a sequence of logic waves, we'll display a group of fields in a terminal. With some thoughtful programming, we can directly manipulate components, aka instantiations of modules, react to property values on components, trigger specific events, inspect and manipulate memory and registers, override the simulation, control processor speed, and manipulate control signals, just to mention a few. A word of warning though, I didn't create a program that is a work of art. I focused on functionality over complexity. There are certainly better ways to organize code via design patterns, but that's not the intent of this series. Along the way, we'll realize a few things. For example, Verilator knows nothing about our C++ code, or NCurses for that matter. The CPP code is simply a black box. The two worlds don't know of each other, but they can influence each other. Another example is the time step versus the eval of Verilator. Time step is just a variable. It's simply an artifact of our CPP code counting how many times we called eval and how many times it's occurred. Verilator doesn't know or understand time step. On the same side, the eval time is based on the HDL's time unit ratio, or the time step is counting HDL's time unit property. So with that in mind, let's take a look at how I've laid out NCurses. You can think of our console program as broken up into three separate units: the console test bench, the simulation, and the console. You can see here in the background that the NCurses is displaying all the control signals, some registry files, and memory. And the way this works is you have the console test bench, and it is stuck in a loop that's going around and around, and as long as the step count, a variable we have defined in our C++, is less than some larger number, then we'll increment or call the simulation one time. It'll go around. So if we set the step size to 1,000, then it'll run 1,000 evaluations in the simulation and then stop. Simulation file has all the things in it for, say, running up to a fetch, and you can continue fetching the next instruction one after another, or even running up to an e-break, a specific instruction. You can do a bunch of run-tos, or running to a specific program counter value. Console is probably the larger of the three, and it has all the NCurses libraries. This is NCursor, and it is a relatively simplistic library to use, but it will manipulate a terminal. And as you can see in the background here, we're manipulating the colors, the bold versus normal text. We're positioning it precisely where we want it in the display, highlighting different types of colors here and there. And then what you have is NCurses will interact with the keyboard, and then it can interact with the terminal itself. And between those two, you get a console program. Now, the way NCurses is to work effectively with a console program is you need to turn off the blocking portion of the code that reads the keyboard. We don't want our simulation to stop every time we're trying to read a key from the keyboard. So let's take a look at the code that implements all of what you're seeing right here. We'll start by looking at the console test bench. And again, this isn't really about C++ code or libraries or anything other than RISC-V ISA. So I'll keep it relatively brief and at a high level. So starting at the top, Here is that time step value that I was speaking of, and we increment it every time we call eval. This is the bridge between, it's not really a bridge, it's a gap between Verilator, which is on this line, and my simulation code or control code on this line. Neither one of these knows of each other, so I'm tracking every call that I make to eval. And each call to eval, as mentioned before, is executing one time unit of the HDL code. And we'll take a look at that shortly. We've got some variables used to control the console, the test bench. We instantiate our console NCurses stuff, initialize it, start it, and then show some of the variables on the display. Then we instantiate our simulation object, which contains routines in it that will run the simulation according to the step size and the step count. And then we have this relatively large command switch. If I collapse it down, you can see that it's the biggest portion of the test bench itself. There's nothing really important in here other than we call the console handle input. We'll talk about that in a moment. And it responds with a command, and then depending on what the command is, we do something with the simulation. So I'll collapse that down. This is the core of the test bench right here. And as long as that step count is less than some sort of big number, step size, then we'll run one iteration of the simulation. So we'll call simulation begin, we'll run Verilator's evaluate statement, then we'll show whatever happened, and we'll update our console's state variables. Otherwise, we run the simulation end and we say we're not running anymore. Eventually, the user will issue a command to exit the while loop, setting this to false, and we'll fall out, deleting everything and shutting everything down. That's the test bench as it is in and of itself. The real heart of the console is in the next two files. Now we look at the simulation component, and it is where we do more complex controls of the Verilator or the Verilator simulator. For example, we can implement the reset sequence, which is setting the reset signal low, activating the reset line on the processor, setting up some of our own CPP variables, such as that step count, and then calling the update method. And in this case, we're going to set our step size equal to 3 full cycles. In our processor, remember, we have the rising edge and then the falling edge where we do work. So we want at least 3 cycles to occur to make sure that we've gone into the reset state. So we'll go into a loop and we'll call begin with our model. That's on the simulation. We'll call the simulator to make one time unit step, and then we'll update our model again, and we'll keep doing this as long as the step count is less than the step size, which again is 3 full cycles. So if our cycle is 20 units, then we're going to do this loop 60 times. And then when we're done, we set the reset inactive to false, and then we end our reset by updating the display to running as false, and we deactivate the reset signal. From here, we're now going to, the simulation Verilator should have moved and been prepared to go to sync 0, which we saw in previous videos. We can also do stepping for standard stepping, which is what we were doing up here. We were calling the begin, which is right here. And again, it's based on our model. We can count how many times eval has been called, and we know that our cycle, a half cycle, is 10 units and a full cycle is 20 units. It's simply what we set up on the CPP side. Again, Verilator only knows the time unit steps and their arbitrary units. Our CPP code thinks of them as nanoseconds. And we know that a half cycle is 10. So every 10 eval calls, or 10 nanoseconds as we interpret it, we toggle the clock. That's the biggest distinction is that Verilator really only looks at the time units inside the HDL, but it really doesn't care what the length is. It's us as human beings that really want to know what that time unit is for our own reasons. And then we call update, which we grab the current state of the clock versus the previous state so that we can update the display with a rising edge or a falling edge symbol. This is more aesthetics than anything. We're incrementing our step count, and eventually it will exceed, if we come back up here, the step count will exceed the full cycle if we're doing a reset in this case. We can do other things. We can run to a fetch instruction. So if we look at that one real quick, we know that if we're already in a fetch, or we've already hit a fetch, we need to move past it. So we'll go to the decode statement. Once we've gone past it, we can then start to look for the next fetch state. Now I've added in this max step just so that we guarantee that we don't run on. This is a termination feature right here. We can also do a run to decode, which is doing the exact same thing, but instead of looking for the fetch, it's looking for a decode down here. And the same thing, we can run to the execute statement. We can run to a specific instruction. In this case, I'm running to the e-break instruction. And I arbitrarily selected 1,000 so we don't run on forever. If we never find a break, or our program never hits a break because it's unreachable, we just simply try 1,000 time units to find it. And by that, we take the instruction register itself, we grab it here into a string, we break it down by grabbing the opcode out of the string. Now remember that strings in C++ are from 0 to 31, but our instruction for RISC-32 is going from right to left, from low bit to high bit. So our numbers are a bit reversed here. And if we identify the specific e-break signal and the bit 20, which is actually bit 11 in our string, is a 1, then we know we've hit the e-break symbol and we break out. So that's what the simulation does. It can just basically run through. And again, if we want to search for a specific target program counter value, we can set it up and run that. So this is what the simulation provides for us. And finally, we look at the console portion of the application. And this is the largest one. It's nearly 1,000 lines of code. And again, I'm not creating a work of art here. I'm doing what's necessary in order to run our console application. And what it does is it drives the display and interacts with NCurses. We have the init. And here is the most important lines when it comes to dealing with NCurses and our console application. We need our console to continuously run in a loop. We can't afford for it to halt and wait for a key to be touched on the keyboard. In order to do that for NCurses, you have a couple of options. These are the two most important. We want to grab and include control sequences like the up and down arrow keys for scrolling through memory, and we want to enable non-blocking, and this is the critical one of all. By running this line, we tell NCurses to not wait at the key for any keys to be touched. It's basically polling, in other words. And of course, we don't want NCurses to echo keys for us. We want to echo those ourselves by moving them to specific locations on the screen. And then raw means we don't want any interpretation of the keys themselves. Then we throw in a couple of checks determining whether our terminal supports colors, which most Linux consoles do today, and we define some colors. But again, this is the most critical portion of the console application here. Without this, at least without this one single line right here, we really couldn't use NCurses. So this is how you initialize NCurses. From here on out, it's just a bunch of giant methods for controlling the cursor and placing text wherever we need it to be. Here's the input where we read, we call the get character, and because we set to no pause, this call will not pause. It will call this. If there's a character, it puts it here. If not, we move on. And then of course we interpret every one of those characters, keys up, keys down for scrolling through memory. If they hit the return key, we bundle up any of the information into arguments and parameters for the console itself to interpret, and we keep moving on. So you can see how big this program can get if you're just trying. It's literally, we've created an application using NCurses. And here is all the show methods for showing integers and booleans, registers in binary format or integer, clock edge. In this particular case, we're literally drawing a clock edge, either rising or falling, using the extended ASCII characteristics of NCurses. CPU state, we have interpreting values into strings and placing them in there and changing their colors to a yellow on gray. You'll see that in the images. And even more stuff. Here's showing memory. We take a memory bank that came from Verilator itself, and we begin iterating through it one step at a time, interpreting memory, converting any ASCII type codes into text itself, which you'll see in the memory display section. Same thing for the PC marker. We're moving it around using variables to track where it is in the display. Again, this is literally writing a GUI application at the terminal. We get commands for arguments. The console will want to get at these commands from time to time, or these arguments from time to time. And that's it. You can see that it's quite a lot of code. It's upwards of 1,000 lines of code, almost 1,000 lines of code. And it's the biggest, not complex, but bulky of all the code. And we're always including the NCurses library. This is the second most important thing you need to do, is of course include the NCurses library. And there you go. That's the console. Now let's go back to the console and look to see how those arguments that we've entered in using the specific commands, and look to see how they modify the simulation itself. They're bypassing the simulation. In this case, if I type MM at the keyboard and then a specific address, space, and then another and a value, well, the address comes from argument 1 and the value that we want to write. This particular line is bypassing the simulation. We're taking the value and injecting it directly into the BRAM that is inside the memory module. This is the equivalent of modifying memory. The difference is that we're injecting the value directly into the memory versus, say, using the processor running a program, say a monitor program, issuing commands that the monitor program recognizes and placing it into memory. This is bypassing that. We're directly modifying the model itself unbeknownst to the simulation. The simulation would have no idea that some external black box took a value and injected it straight into memory. We can see that further down here when we issue the command for loading one of our RAM modules here. Again, we're reading argument 1 has the name, the prefix of the file itself. We're using C++ basic stuff here where we read in a file, we check to see if it's open. If it is, we use regular expressions to split every line up. We expect there to be an asterisk. If we looked inside of our RAM files, we know they're full of lines that have an address and a hex value. We break it apart, we use regular expressions, split them into matches, we grab them, and here we are again, directly injecting a value into a memory location. The simulation is effectively stopped at this point, so it doesn't know that there is a C++ program that's going through and modifying memory. That's how the CPP console application works. In the future, we'll write a monitor program using the interrupt features that I was talking about to do the same exact thing, but this time the processor is running a program called a monitor that will take values and put them into memory. So this is an example of how we bypass the simulation and directly manipulate it. And we can do much more, and we can set the program counter, processor instruction state, or even memory state. It can sometimes do real well, or you can confuse the processor doing that. It's a double-edged sword. So this is the console. Now before we start interacting with the console and loading programs in, let's take a look at the makefile, which puts it all together. As it's slightly different than the other makefiles in that we're now including NCurses and not GTK Wave. So you'll see that I've removed any kind of element of GTK Wave out of this. We have our usual top module, we have the test bench, which in this case is that console, the simulation, and the test bench itself, some utilities for converting things like strings and integers. We have the test bench module file, but it's slightly reduced, so it's a separate one in and of itself. And then we have all the headers that drive everything. The indices for these are all very specific to NCurses and how it controls it. Then we have the HDL code. We've been through this over the last series. This is all of our modules. This is the real deal right here. This is the HDL. And then we have some stuff we've already seen, the build directory, the toolchain, the simulation, which is Verilator. And then finally we get down here to the real meat of the makefile. And that is, to run the console, we need to do things broken up into pieces. It's slightly different than the other makefiles, which included both the executable and build in the same line. There used to be a build command right here. But we're not doing that in this particular one. We're going to take that back out. So in order to run the console, we need to first run and construct a makefile, and Verilator's build system will do that using the execute command. This command right here will generate a makefile, which will then do on the run make. And to speed things up, I'm using all 4 threads on my CPU. We're changing directories into our build directory, and we're going to run that makefile that was generated in this phony right here. The reason why we do this is so that we can pass in additional flags for NCurses. It's very difficult to tell Verilator to include other directories if they're not very specific to Verilator itself. At least I haven't figured it out. So the other way to do this is to break it up into 2 steps. First, create the makefile that's specific to Verilator, and then execute that makefile with the additional dependencies that we need, which is the NCurses library. And then finally we run it as we have always done, by moving into the build directory and running the executable that was created. So now we're ready to run the console itself. To familiarize ourselves with the console, we'll start simple and run the load word program. And you can see here we've already covered it in GTK Wave. We'll be loading X1 with the value that's at address 28, which is dead beef, and then we come to a halt. So I've already loaded that up into the RAM, and we'll run the console. So we've come over to the console, and we'll run the make console command, which will run all 3 of those things. And up pops the NCurses console. We're showing all of the variables of the processor itself, the ALU, any loading flags, the multiplexers, all the data, the instruction state, the 2 RSA register file and B, memory writes and reads, the program counter information, our states, the next state and our vector states, whether the CPU is ready or reset, a clock signal, and whether the simulation is running. And over here we have all the registers, all 32 of them. And down here is a specific representation of these registers, the active one, whatever is active. And in this case it's X0, so we see the binary representation and the integer representation. Over to the right we can see the memory and any ASCII values that it might determine exist. 73 just happens to be the lowercase s in ASCII, and our PCB, our prior and our PC are both at address 0. So let's go ahead and load in the load word. We used the command LD and then the name of the RAM file, which is LW, and you can see that it's loaded up top here. So at this point we have a bunch of commands that I can run, and again it's nothing specific to the RISC-V ISA, so I'll be relatively brief about that. But you can see that I've loaded that program that we saw moments before. We have the load instruction itself and then break. So what I'll do is I'll just run forward to each fetch cycle. So I'll type in RN and FE for the abbreviation of fetch, and you'll see that the program counter has run all the way to the very first fetching of the first instruction, which is right here, the load. Now at this point I could actually step through one time unit at a time, which I can do here, type NS, and now I'm stepping literally one time unit at a time, which we can see up here. But that's a little cumbersome, so we'll go ahead and run at full cycle. So that would be 20. So there's a full cycle. That's one whole clock, a rise and a falling edge, and you can see over here that we're running through the different states. We're at the decode state. If I hit return again, It'll run again. We get another clock and it's moved to the execute state. So it's just executed the load, and we should see dead beef loaded into the X1 register as soon as we move through all the cycles of the load word. And you see that we move through all of them right here, and now we see that X1 has dead beef. So yes, this program is running, and now we're at the break and we're stuck there. This is the black hole that we see. You can see that the clock is moving up and down. I'll do a half cycle so we can see that clock going up and down. Now it's high, now it's low, rising up and down, and I'll slow down even more so we can see it rising and falling. There it is, rising. There it is, it's risen. We're on the rising edge of the clock. Now we're coming down another 10 units. Now we're falling. And that's how the console tool works. We can see that all of our registers have been loaded with various things, where our instruction is now in the black hole of the e-break, and we're at various other states while we're in it. So let's go ahead and run the next more complex program. Our next program is the XOR. It's a demonstration of using one of the ALU logical expressions, and we'll have a little bit of fun where we'll take X1 and flip each one of the bits on and off by XORing all A's with FF, and that causes every bit to toggle on and off in opposite orders. So this is the program. We load in X1 with whatever X4 is pointing at, which happens to be loaded with 28 via the initialize block in HDL, and we'll load in X2. So we load X1 with A and X2 with F's. Now we're ready to run this program. Again, it'll run the XOR, and this program will never end. So once we start it, we will have to stop the processor once we get it going, and we'll see that when we're running it in the console. So let's flip over to the console right now, and I'll bring that up here. We'll go ahead and load in the XOR program, and you'll notice in memory it is loaded. There's the 22, there's the load word for X1, X2, the XOR machine code, and then down here at A is the right here, yeah, A is all the A's and then all the F's, and we're ready to go. So I'm going to go ahead and start off with running the fetch, and we'll see how it moves to each one. In this case, we're going to load X1 with all A's, so there you can see A has been loaded with all A's, and X2 should transition over to all F's. So we'll run it one more time, and there it is. So we're doing good so far. The next time we're going to now execute the XOR instruction. So to see what's happening, let's go ahead and come down here and set our active register to point at 1. And there you go. You can see that it's all flipping back and forth. We can ignore the integer part because it's not really representing what we want to see. We're focusing on the binary, and we should see every one of these bits flip every time we exclusive OR A with F. So let's go ahead and run the fetch here, and you'll see that, whoops, gotta run the fetch, run fetch, and there you go. You can see they've just flipped as we go around, and we're jumping backwards. So that's one thing to understand about the jump instruction that we're executing, is this jumping. Now I'm going to go ahead and let the program free run, so I'll type in a really big step number, and you can see that it is now running down below. You can see the register flipping the bits back and forth. I'll speed it up a bit by changing the time step, and there you go. Now it's running a little faster. We can see that it's rapidly running through all of the states in the processor, loading and unloading values in registers. And you can see how it flips back and forth between plus. Now in this case, it's just happened to flip between the same number as it goes. And there you go. This is our first free running program as it loops around executing our program. And you can see that the X1 register is flipping all of its bits from A to 5. Excellent. And we can halt the thing if we'd like. And there it is. The next program we'll take a look at is the jump and link register instructions to see how it manipulates the X1 register based on a jump instruction and then comes to a break. We know that if it jumps to this address right here, it should load X5 with the correct value, which in this case is what's at address 24. If it doesn't jump correctly, it'll land here. So we'll need to also pay attention to where our break that we hit, it either is at 2 or at C. So let's go ahead and take a look at the program in the console. So here we are back at the console, and I'm going to go ahead and load in the JALR RAM program. There we go. You can see there is our JALR instruction, the break, and the data that we'll be looking at is down here. And at B, we have our other instruction with another break. So let's go ahead and step through it. This time we should see X1 loaded with the next address. So we'll go ahead and we'll do a run fetch. And let's take a look at, so there we are, we're sitting at the instruction, and we'll fetch one more time. And as you can see, X1 has been loaded with the return address. We're not using it right now, but X1 now contains the return address, which is this instruction right here, address 2 in word address format, or in byte address, that's 8. So we know that things are working good so far. You can see that the program counter has jumped to the address B, and there it is. We'll execute that one, which loads in X5 with the appropriate value. There it is, the 0100, so it loaded it from here, 24, into this address is 5. Excellent. And of course we execute the last one, which is the break, and now we're perpetually breaking at that instruction. So there you go. That's the jump and link register. Now let's take a look at an example of the branch instruction. We've seen this before in the GTK wave example, but now we're going to look at it from the console's perspective. We'll load X1 and X2 with two particular values. We'll compare to see if they're not equal, and if they're not equal, we'll jump to the offset address. So we should see our program counter change to address 6. If they are equal, then it'll run this instruction and break. Now, having seen this in GTK wave, we know it's going to take the offset and go in this direction. So let's go ahead and take a look at that in the console here. So I popped it open, and we'll go ahead and load in the value for the branch on equal, or in this guy mislabeled it, but it is the branch on not equal. So here we are. We see it has loaded in our two load instructions. There's the program as it is, and some of the data is down here in the C and D address right here. So as usual, we'll do a run fetch. Now I don't have to do a run fetch. If we want to see this step by step, I can do a full cycle step. So here we are. We've now moved the PC down to here to address for our reset vector. We're literally going through the reset sequence at this point, because you can see that our CPU state is in the reset and we're at vector 0. I'll hit it, do a full cycle again. We're now at vector state 1. One more full cycle takes us to 2, which loads the program counter with the address of the first instruction. And then we'll do another one, which sends us ready for the fetch instruction. And we'll then go ahead and fetch it in, and you can see that we've loaded in X1 with the value that's at 28, which is 5. And so X1 has 5 in it. Excellent. Now at this point we just went through it, and we can continue to step one step full cycle at a time and watch it go. And there you go. You can see it's running the load instructions. Here's the sub instruction state. So it's running load instruction. It completes. Excellent. And we'll keep stepping here. That's exactly what we're expecting. So I got a little bug here. It's showing didn't wipe out enough characters, but there it is. And it executed the program. So we know that our program counter should be sitting at address 4. Or in this case, it should be sitting right here. And it is. It's hit the, we'll go a little bit more. And there you go. We're executing and executing, and we're stopped. Excellent. We're at the break. So how about counting up, or counters in general? In this case, we're going to load the X4 register with the base of our data, which is 3C. So if we come down here to 3C, here's the address of the data section. And there's our data, the max count we're going to increment by, and the counter starts at some specific value, like 1 in this case. We load those into our respective registers, and then we begin counting. So we add x3 and x2, x2 being the incrementer, and we store it back in x3, our counter here. Then we branch if x3 is less than what we're trying to count up to, so we'll keep going around in circles right here until we're finished, and then we'll hit our break right here. So let's go ahead and give that a shot in the console. So bring that up, and we'll load in the program. There it is. It's been loaded in. And we'll go ahead and just run the fetches on these so that we can see each one going. There it is. It's gone past the reset sequence, and it's sitting at the first instruction. So it'll load x4. So we should see x4 load with our base instruction. And it has, which it happens to be already at 28. It pre-populates with 28. Then we'll go ahead and load x1, x2, and x3. So x1, x2, and x3, there they are, 5, 1, 1, and we start off. x3 is going to be our counter. And now we'll add them together, and x3 should bump up to 2 when we run it. There it is. It's now 2. So we can see that it's 2. We'll keep watching that, and it'll jump up and do it again, 4, and 5. And it's finished, and it hits the break statement, and we're done. So there it is. There you go. It's operating as we expect. We were able to. I can slow the stepping rate down and look at all the intricate substates that it's going through as it's doing that. But we'll try that on some of the more complex ones. Let's try something different. Shifting a register left and right repeatedly, much like the Cylon effect that I did with the A09, but we'll see it in the console this time. So as usual, we load in our x4 with a base pointing to our data. We load our various registers with the pieces of information that we need. X5 will have the left pattern, X1 will have the right pattern, what our starting pattern is, and then how much we're shifting by, which is 1. Here's the shift left logical, and here's the shift right logical. And we'll bounce around running each one of these loops here, and we'll never exit. This is an unreachable value right here. So let's take a look at the console and see how this is running. Bring up the console here, and we'll go ahead and load it, and we're going to set our register that we want to watch in binary form to x3. So we set that there, and so now our register is reflecting in binary and in integer what the value 8 is. So we'll go ahead and we're going to start this thing running, and we should see that x3 is shifting left and right. We'll see the 1 move all the way over to the left, bounce back, move to the right, and back and forth. So let's get it started. We'll type in a really big number to let it run on. And as you can see, it's setting up, loading in all of our registers with the values that it has. You can see they're loading up. And now we're beginning into our loop. And here we are, we're going through the loop. And you can see the 1 is moving. Now it's moving pretty slow. So let's change the delay of each time unit. For example, Verilator is always running at 1 time unit, but our console is set to delay for every nanosecond. We delay 10 milliseconds. So I'm going to change that to 1 millisecond so it runs a little bit faster. So there you go. You can see the 1 is going to make it all the way to the end and then bounce back and go to the right. This is what I call the Cylon effect. Now at this point, we can do something that you normally couldn't do, and that is we're going to stop the processor running, so now it's halted, and we're going to make a modification to a registry that changes its functionality. And in this case, we're going to modify the left pattern where it actually stops. So let me start it going again. Here, we'll let it get all the way to the left, and we're going to change the pattern up a bit. I'll halt it again. There it is, it's halted. And this time, we're going to change the pattern on the left, which is X5, right here. It's 80000. And we're going to move the 8 right here. So again, the Verilator does not know we're doing this. In this case, Verilator is halted. It is not running the simulation. I've halted it. So I'll come here and do a change register, or change register. We're going to change register 5 to have the value 8 0008 0000. And we'll see that X5 is going to move the 8 right here. So we'll hit return, and there's the 8. So now when the 1 comes back around, it's not going to go all the way to the left. It's going to go much shorter. So now let's start the simulation again, right here. And you can see it picks up, and it's going to bounce around, and it should stop when it hits that 8. And there it is. So the processor in this case doesn't have an idea that we've modified the state of a register while it was, quote, technically running. We paused it, modified a register, and then restarted it. And that's kind of how simulators give you a little bit of superpowers over your modules in your Verilog, or your HDL in this case, code. It's a very nice and handy debugging tool to debug your processor, to get in there and be able to manipulate it on the fly. And as you can see, this code is never going to end. And as you probably guessed, we could go in and set the program counter to manipulate the state of the machine while it's holding. As a matter of fact, I can actually change this value while the simulator is running, because my console will change. It doesn't have to be paused. As a matter of fact, if I wait long enough here, so I'll go and do a change register to 5, and this time we're going to set the value of the register to 0080, 1, 2, 3, 4, like that, and we'll change it. And now X5 is even farther. So now you can see while we were running the processor, it now goes farther over here to the left to run. Now if you really want to see this thing move fast, I can turn the delay off between each instruction, and that's what I'm going to do. I'm going to change the instructions so that we don't see any delays within the processor itself. So I'll come over here, and I'm going to look at what I forget what the change command is, the enable the delay right here, delay time, delay off. There it is. So it's delay off, and you'll see that now it's really fast. You can see that it's running at full speed right now. There's no delays. Now this is still not as fast as the simulator can run, because there is now a delay with the display itself. It takes time to update the terminal with its values. So the simulator can technically run even faster than what it is right now. So you can see that it's moving so fast we can barely see the ones moving back and forth. You can barely see the program counter flickering. And you can barely see the clock moving. So I'll put the delay back on. And there it is. It's now moving slower now. And this is as fast as you can run it with the delay on. 1 millisecond is the smallest I can pass to NCurses for its delay. Now I could change that by calling the OS's version of thread sleeping, but it is what it is. So there you go. Now we'll take a look at subroutines, and this is the program we'll use. Again, we're loading in the base address of all of our data and to load into X1, X2, and X3. This is our jump instruction, which will jump down here into our subroutine. It'll do an increment, and then it'll do a return based on X5 plus 0 and return back up to this instruction right here, the branch on less than. So this will go round and round. We should expect in our console to see X5 loaded with the number 18, or in our case in memory, it would be address 6. So let's take a look at the console and see that in action here. So I'll bring up the console. There it is. We'll do a load of the subroutine module. So let me restart that here. We'll load in the subroutine module. And now we're ready to go. So I'll do a run and fetch. So basically it'll run until it hits the fetch state. And there it is. It's hit the fetch state as usual. We'll continue running until we're running through loading in each one of the instructions. So if we look at our registers, they're loading up. There's a 1 into X2 and a 2 into X3. So we're going to just count the 2 in this case. And then you'll notice that the X5 has the return address loaded into it. So down here, when we get to the JLR, we'll jump back to address 6, which is equivalent to address 6 word address and 18 byte address. So we'll step again. We'll see that it jumps back up here. Sure enough, it did. And we go through this until we hit the end of our count cycle and hit the break statement. So this is executing just as we expect. Also notice that our flags were changing down here. We were on N and C for the branch and less than. As soon as that doesn't happen, the Z flag is set in this case, doesn't mean anything. But the branch and less than is looking at those two flags. Remember when we were going through the HDL code in the control matrix for the BLT instruction? It's looking at specific flags from the ALU, and it was doing exactly what we expected to do and what we saw in GTK Wave as well. So this is an example of a subroutine. We incremented the X3 register, which has 5 in it. Excellent. And everything is working as expected. Now we reach one of our more complex programs, and that is comparing two strings. And I have two down here. We have beef and def, or def, whatever you prefer. We again load in our register, base register with the data we'll load. We load them into all of our operating. X3 will point to the first string, and X4 will point to the second string. X5 is counting how many characters we're comparing, and X2 has the length of each one of those strings. We then fall into loading X6 and X7 with the bytes that are pointed to by X3 and X4. We increment our index pointers, X3 and X4. If the X6 and X7 are not equal to each other, then we immediately know the strings aren't equal to each other, and we jump down to the no equal section. Otherwise, we increment X5 to then branch on less than. We check to see if X5 is less than X2. If it isn't, or if it is, we make the next loop, and we'll go round and around doing this until X5 is equal to X2. At that point, we'll load X9 with a 1. So in our case, if X9 has a 1 in it, then that means they were equal to each other. If X9 has a 2 in it, then they weren't. So let's go ahead and make sure that they're equal to each other. Set that there. We'll go into our str program and make sure that both data are equal to each other. Save that. And now we'll come over to the console and run that out. So we'll bring that up. We'll load up our string. There's our two ASCII values right there, beef and beef. We've loaded up our program and we're ready to go. So let's take a look at that. We'll do a run to fetch as usual. And there it is. It's at our first instruction, which is loading in X4. So X4 now has 54 in it, which in our case is the 15, address 15 beef for word address. And we'll keep stepping through, loading in each one, X2, X3, X4, and you can see X3 and X4 indexing into the data down here. And we'll load, clear out X5 is now clear. And now we're going to load X6 and X7 with what the pointers are pointing at. There's 46 and there's 46. Excellent. And then we will do a check for X7. It's not equal. We'll increment X5, and that's what happened. And so now we're coming back up to go back up to the top, and you can see that X5 has been incremented to 1. And now we're doing this over again. We'll now load X6 and X7 with the next character in the array, and we'll go around loading in one character after another, and eventually we finish comparing all the strings, and X9 will have a 1 in it. Excellent. Now let's go ahead and modify memory to contain the not equal values in it. So we'll reset memory and reload. So we'll reload our memory and start over. So now we'll reset the simulation. So I'll do signal reset. Now it's reset. And I'm going to go ahead and modify the memory 16 with a different text string. In this case, I'm just going to change the B to a D. So I'll modify 0x16, that's address 16, with a 44, 45, 45, 46. And, let me try that again. So I'm going to modify memory location 16 with a 0x44454546, and there it is, DEEF. Now let's go ahead and run the simulation again, FE, and we'll run through, and this time X9 has a 2 in it, just as we expected. Excellent. And finally, I thought we'd have a little bit of fun doing the Fibonacci sequence, and I've listed out all of the numbers that up to about the 27 in hex value, which is this one right here, and we will be adding those up in the X3 register. So the way it works is I load X1 and X2 with the starter numbers 0 and 1 up here, and then I set X4 to count how many of these we're going to do up here. And then X5 is counting up to that number. So to do the Fibonacci, you sum the X1 and X2 together, which is 0, 1, and we get that, and that's placed in X3. Then X1 becomes X2, X2 becomes X3. So effectively we're scooting right along here in pairs of 2, and then finally we move, we increment X5, and then we branch back around here, and we keep doing this until X5 is no longer less than X4, and then we break. So it's just a simple way to do the Fibonacci sequence by summing the previous 2 registers and then shifting them, if you will, in values through here. So let's go ahead and load this up. So I'll bring up the console here, and we'll load in the Fibonacci. There it is. We can see our instructions. There's the adds, and here's the branch, and then finally we have our e-break instruction. Now in order to see the values, we're going to highlight our activate X3 so that we can see the integer value of it. So we'll do set register 3. And so now we'll be watching this field right down here as we run the Fibonacci. Now I'm going to run this, I'm going to set the delay time to much shorter, and we'll start the program off, and we'll just give it a hefty amount of values here, and watch this value right here. It should come up to be the last value that was in our Fibonacci sequence. There's 1, 2, 3, 5, 8, and there it goes. It's counting up. It's doing the Fibonacci sequence right there. 277, 41, 81. There it is. 67. There it is. And finally, we're reaching the last one right there, and it's finished. That was it. That was the Fibonacci sequence. Excellent. Now, if we look, we can see that X5 is 1B. That's what we had loaded in the 8 right here in this instruction on line 3 right here. This one loaded the 1B right there. There's 1B, and we can see it. So let me halt this so I can highlight it. So there's 1B right there, and there's 1B. We counted up to it. Excellent. We terminated at the right location, and everything is good to go. We just did a Fibonacci sequence, and we'll walk to it. So excellent. We can now precisely control and run the processor right down to the time unit scale. And I have to admit, it's pretty cool that we can single step through the processor, inspecting and modifying the core. And this will come in very handy way down the road. Now at this point, you might think that the simulation is complete, and you're right for the most part. However, I'd like to add one additional piece of functionality to our simulation, and that is memory mapped I/O. This allows the data to enter and exit the core without bypassing the simulation, and it gives us the ability to interact with the running programs, as opposed to what we've been doing so far, which was directly modifying registers and memory and states and everything else. A good example of that would be a monitor program, to be able to act with the monitor program and change memory versus bypassing the simulation and directly changing memory. Thus, in the next episode, we'll look at implementing the interrupts and perhaps a real implementation of the e-break instruction. So until next time, peace.